Hi, my name's Teddy, and this presentation seeks to explore a small corner of the world that is tissue engineering. Firstly, let's go through some basics and take a look at the unique characteristics and structures of bone. Bone is a heterogeneous composite material comprised of two major components: hydroxyapatite crystals, the inorganic phase which withstands compression, and type 1 collagen fiber matrix, the organic phase which resists bending. The relative proportions of these components depends on age, gender, and any afflicting metabolic bone diseases. Bone has impressive mechanical and physiological properties, acting as a scaffold for musculature, a protective surrounding for vulnerable organs, and as a reservoir of ions. Bone is a metabolically active organ which is subject to constant restructuring through cellular action. This unique process of continuous remodeling enables bone to adapt to changing external physical stimuli and to self-heal without buildup of scar tissue. The two most distinct macrostructures of bone are termed cortical and cancellous. Cancellous bone is the sponge-like interior structure with high porosity. This porosity has multiple benefits, but limits compressive strength. Cortical bone makes up the tough outer layer, which provides the majority of a bone's mechanical strength. It is much less porous than cancellous bone, and because of its higher density, cortical bone accounts for roughly 80% of all bone mass in a human body. It's important to note that the disparity in compressive strength between these two macrostructures must be considered when manufacturing materials for bone repair, or else complications such as stress shielding could occur. For example, if cancellous bone is repaired using a material with compressive properties more similar to cortical bone, then the bone surrounding the implant could begin to atrophy under reduced stress. Diving deeper, we observe two very different microstructures present within these macroenvironments. Cancellous bone has a microenvironment containing rod-shaped trabecula, which form a porous open lattice. This porosity enables high metabolic activity due to increased nutrient flow and improves the ability of cancellous bone to absorb shock. Cortical bone has a much different structure, comprised of densely packed tube-like osteons made up of concentric lamellar cylinders. There are three main osteogenic cells which make up the so-called submicrostructure of bone, which are responsible for bone growth and the previously mentioned remodeling processes. These cells are osteoblasts, which are responsible for bone formation, osteoclasts, responsible for bone resorption, and osteocytes, which are mature osteoblasts contained within the osteoid or unmineralized bone matrix that they secrete. These osteocytes are hypothesized to control homeostasis within the extracellular matrix by moderating osteoblast and osteocyte action. The nanostructures of trabecular and cortical bone are very similar, both consisting of collagen nanofibrils which are mineralized through the growth of hydroxyapatite crystals. These nanofibrils form tightly wound bundles which provide bulk bone with much of its mechanical strength. Tissue engineering is a multifaceted approach to bone graft development, which incorporates chemical and physical cues to mimic the described natural bone. It combines the innate reparative properties of human osteogenic cells with the strength and rigid structure of synthetic scaffolds. Several properties have been identified as essential for effective bone regeneration and must be met by engineered tissues. An engineered tissue should elicit no unfavorable tissue reaction, or in other words be highly biocompatible, be biodegradable, have high mechanical strength, and be relatively cheap to manufacture. An area of particular interest is the use of nanoscale surface modification to influence bone regrowth, because the interactions between cells and nanostructures plays an essential role in the control of various cellular functions, including proliferation, migration, and formation of new extracellular matrix. The importance of nanotopographies is due partly to their ability to upregulate stem cell differentiation and hence promote osteogenesis. Also, osteoblasts will align with nanogrooves of appropriate dimensions, demonstrating the ability of nanotopography to influence the macrostructure of bone and hence bioactivity of bone grafts. Moving on, let's take a look at a promising candidate in tissue engineering, silk. Humans have been exploiting the beneficial properties of silk for thousands of years, with the first recorded explicitly medicinal use dating back to roughly 160 AD. Processed silk fibrone has quickly become the subject of extensive research due to its impressive mechanical properties relative to other biopolymers, and also its tunable biodegradability. A secondary benefit, stemming from silk's use in textiles, is its high availability at a relatively low cost. Silk is also non-toxic and non-immunogenic, making the likelihood of implant rejection appropriately low. Raw silk consists of two fibrillar protein strands known as fibrone, encased in a sheath of the globular protein sericin. Fibrone can be fabricated into a variety of scaffold structures, but first the fibrone must be freed from the sericin coating through a process known as degumming, whereby an alkaline solution is used to cleave peptide bonds. This process is unselective and often leads to degradation of fibrone, which reduces its mechanical properties. Therefore, less harsh and more specific degumming methods are being developed using enzymes. Fibrone consists of a complex arrangement of interlocking nanofibrils, similar to the nanostructure of bone, and it's the friction between these nanofibrils that confers a great deal of mechanical strength to bulk silk. Antiparallel beta sheet crystallites, the predominant secondary structure in fibrone, embedded within a less ordered amorphous matrix comprised of random coils, beta turns, and alpha helices. The high density and rigid ordering of beta sheet crystallites allows for effective absorption of impact pressure through distribution of stress over the matrix as a whole. The specific arrangement of beta sheets also explains the exceptional tensile strength of silk fibrone, as under lateral load, crystalline regions on adjacent peptide chains interlock and evenly distribute the applied stress. Silk fibrone alone does not have sufficient mechanical strength for load-bearing applications, and so modern approaches revolve around the use of composite scaffolds, which combine silk fibrone with inorganic material. Another method is the use of silk nanofibers as reinforcement for scaffolds. This approach allows for the creation of biomimetic implants with matrix stiffness and surface roughness characteristics similar to native bone. Although brief, I hope you'll take away an appreciation of tissue engineering as a powerful tool in the fight against bone damage. Silk is just one route to be explored, but there are so many possible materials, be they natural or synthetic, which can be applied to bone grafting. Thanks for watching.